Hello again, everybody. My name is Janna Lipenkova, and today I will talk about automating taxonomy construction. This is work that we do at my company, Anacode, and today I would like to present it more from a business and product perspective. So I will also give some insights, obviously, into the technical details, but in general, it's late in the day for us in Europe, so let's just keep it light and go through the process very smoothly. So the talk has three parts. In the first part, I will present the business challenge and also a summary of our approach, and will also give you a quick demo of one of the products that we have. Then in the second part, we will go into some basic concepts of taxonomies and the categorization as a very general cognitive principle. And finally, in the third part, I will present the technical approach that we use to taxonomy construction, specifically which is based on lexical relations and more specifically the relation of hyperonymy. So first, for the business challenge. What we are doing at Anacode, so one of the main questions that we get from our clients is the analysis of emerging technologies from online use and discussions. So all of us know that the technological landscape and the technological domain is developing and changing very quickly, and corporate customers who have interfaces to new technologies often have a hard time keeping track of all the developments and also just having an overview over different technological domains. So example domains in which we work are artificial intelligence, cybersecurity, fintech, Internet of Things, and so on. Today, I will be mainly showing examples from AI and cybersecurity. We work mostly with online data, and this means that the data set is highly dynamic because, as said, the technologies and also the companies active in these technologies, they are changing very quickly, and thus the conceptual framework that you lay behind the NLP processing is also changing very quickly. So some of the example questions that we get from our corporate customers, they can come from very different departments and from very different business motivations. So one is, for instance, in strategy and planning, like what are the new trends and technological developments in my domain? That's probably the prototypical question that we get. Then we have competitive intelligence. For instance, are there any new substitutes emerging for my product? This can also be, because we work internationally, it can also be on a global level. So for instance, is there some substitute or someone who wants to leapfrog me maybe on the Chinese market? Yeah, so this really works on a global scale. It can be, of course, for investment. So as I just explained, for instance, we are exploring the AI domain and looking for investment targets specialized on computer vision, and so on. So procurement and basically other departments in the company also. So when we started the company, we kind of had a very simple process, and we thought that we can get away with it. So that was the process. We started with the text, data, large-scale scraping, continuous updating of the data based mainly on online sources. So we use different types of curated press data like general press, business press, technology blogs, scientific articles, and so on. On a project basis, we can also integrate social media, but the general finding is that social media is less relevant for technology domains. Of course, it's very relevant if you go more into the consumer perspective, but if you really want to go into technological details, it's less relevant and less rich in information. Then we apply AI and NLP with a whole toolbox of algorithms, and then we hope to get the technological and the market insights basically for our clients. what we found very quickly here is that this second step, so we can have very high quality NLP algorithms, but still there is a lot of post-processing needed before we can hand in the insights to the clients. So you have to produce reports, presentations, you have to somehow formulate action recommendations, you have to interpret the data and so on. So there was always a lot of manual follow-up. And so the technological solution that we found to this, to reduce the manual follow-up, was basically to add an additional layer here of formalized domain expertise, and specifically in the terms of structured knowledge representations like taxonomies. So that's the simple structure basically. Then on a more complex level, the ontologies, and even more complex than completely specified and filled in knowledge graphs. And as said, today, of course, we will focus on this first point of the taxonomies. So now I would like to give you a quick demo into a very new product that we have. It is a monitor for AI trends and news. So I would like to show it on the one hand to illustrate the technical point of how we use taxonomies in our products, but then also because for some of you, it might actually also have a practical use, because it really allows you, for those who are interested in AI, basically to get an overview over the AI domain, but then also to zoom in into specific topics. So I'll switch to my browser. This would be the interface. So it's, as I said, it's very fresh. We are planning the beta release for next week. By the way, if any one of you is interested to get test access, then just drop me an email. We offer a free test access for the first months of the product. So I'll be just happy to add you to the test group. And here we basically have an overview over the AI domain, this kind of a simple taxonomy. It's not the full taxonomy that we would have in the backend, but still it already shows you a big, a high level categorization. So we have multiple sections. We have here the application section, we have the algorithm section, then we have here hardware and infrastructure topics, we have the libraries, data strategies, and here a very small topic so far, which concerns basically concepts of AI governance. These are the, let's say that's the first level of the taxonomy. And then you can see that in each of the sections, you have more specific topics. So for instance, for applications, we have chatbots, robotics, autonomous driving, and so on. Let's maybe look into something that's a bit more technical. So for instance, the libraries. And then we would see basically these libraries that pop up in the data. The size of each topic signals its frequency in the data, which you can also see in the tooltip once you go on a specific topic. Here you have the possibility, so this is the first level of granularity, a very coarse-grained but very high-level overview over the domain. But then you also have the possibility to drill down into specific topics. So let's say we are interested in PyTorch, and we will go on this topic, and we will come basically to the detail page for PyTorch, where we have a quick summary. Then we have the relevant articles, a bunch of articles basically from the last month. We have additional search filters, and then different aggregations. So basically aggregation by data source and aggregation by time, and some additional context information here. So what are the industries, what are the companies, and then what are some of the other keywords which are associated with PyTorch. So that was a quick overview over this monitor. And as said, so this part, this taxonomic overview basically would be something that we construct dynamically from the data using using the algorithm that I will present then later in the talk, which is very important because, as you know, AI is developing very quickly. There are a lot of conferences. There are also a lot of publications in tech, blogs, and so on. And it's really very hard, I think, although we are very deeply in the AI domain, but it's very hard to keep track of all these developments. And that's why we are really convinced that it's important to have automatic tools to aggregate this information and then also to learn when new developments come up. Okay, let's go back to the presentation, and we will now dive a bit into the more theoretical concepts, and specifically look a bit into the cognitive and the formal and the linguistic also properties of hyperonymy and taxonomies. So first, of course, a taxonomy is based on the universal cognitive principle of categorization, which is the classification of things into categories based on similarities and differences. There have been two main approaches which have been proposed historically. So there is an approach by Aristotle, very old one, but very classical one, according to which, so a very formal logical approach, according to which categories can be decomposed into sufficient and necessary conditions that are shared by their members. Then categories are discrete, they're mutually exclusive and collectively exhaustive, and they are objective, which means that each of us, whether you're in the US or you're in Switzerland or in China, basically all of us share the same categorization. On the one hand, this view is obviously a bit limited and very strict, but on the other hand, well, I have to say that if you present end products to the customers, then sometimes it's even better to have such kind of a more rigid representation of knowledge, because AI and NLP is already complex enough. And if you have a framework that's a bit more strict, then somehow it adds to the, basically to the understanding on the part of the customer. But we don't tell them that it's based on Aristotle. That would be it. And the second theory is the prototype theory that was already in the 20th century, which is much fuzzier, but also seems much more realistic, and where categories are defined by their most prominent prototypes, and membership in categories is graded. So there is this famous example, for instance, of birds, and then you have this prototypical property of birds that they can fly, but for instance, penguins, they cannot fly, but still they somehow make it into the bird category, although they don't exhibit this feature. And also important here, this categorization is subjective and it's rooted in individual experience. So based on your culture, your social upbringing, and also your individual character traits, you actually have the, let's say, the right to have a different categorization tree in your mind. So much more realistic, actually much better if you really want to represent the structure of the data, but also a bit fuzzier and messier than the old good Aristotle's approach. Okay, so that was for the cognitive basics. Now for the formal properties. And here we switch actually to hyperonymy, because hyperonymy is a lexical relation which reflects categorization in language. So basically hyperonymy is a relation between two words, let's say X and Y, when X is a kind of Y. So X is a subcategory of Y. And in that case, we say that Y, the more general concept, is a hyperonym of X, whereas X is a hyponym of Y. Hyperonymy can apply to different parts of speech. So the prototypical hyperonymy is the one on nouns. So for instance, a penguin is a hyponym of a bird, a subcategory of a bird. A war is a subcategory of a conflict, but it can also apply to other semantic parts of speech like verbs. For instance, walking is a kind of moving, jiggling is a kind of laughing, and so on. Adjectives, petite is a subcategory of small, wine is a hyponym of red, and so on. Important detail, hyperonymy, well, actually quite obvious. It's a semantic relation, so it applies at the sense level. For instance, if you have this example of wine is a subcategory of red, then obviously we mean wine in the meaning of the color and not the beverage. Yeah, so this is something that you need to consider if you want to use word embeddings, for instance, to learn hyperonymy. In terms of the logical relations, hyperonymy is transitive. So if X is a subcategory of Y and Y is a subcategory of Z, then X is a subcategory of Z. And it's asymmetric. So if X is a subcategory of Y, then Y cannot be a subcategory of X anymore. And now to the linguistic properties and the linguistic distribution of hyperonymy. So this slide is actually key because it shows 3 points in the linguistic properties of hyperonymy, which we will also pick up later when I present the approach. So the first point, the one that's the easiest to capture, is basically that hyperonyms and hyponyms often co-occur in specific, in quite narrow context windows, and also in specific lexicosyntactic constructions. So we have patterns like X such as Y, so birds such as penguins, X especially Y, Y and other X, and so on. And in a more general sense, we also have the collocations. We will see this later then in the approach, how this works in detail. Then the second point is, so once we leave this realm of co-occurrence, we also have distributional similarity. So if the hyperonym doesn't co-occur with the hyponym, then you still can follow some of their properties based on distributional similarity. So specifically, they tend to occur in very similar contexts. So for instance, if you have automobile and you have the 2 subcategories, SUV and electric car, then all of them can occur with engine because, well, automobile does occur with engine, and having an engine is obviously a very prototypical property here. But of course, distributional similarity is a very broad concept, and it's also a symmetric concept. So, and hyperonymy, as we have seen, is an asymmetric relation, so it's not enough to find the hyperonymy pairs in non-co-occurrent situations. And this is why the third point is important here, which is asymmetry and the specificity of the context. So the observation here is that often hyponyms occur in more specific contexts, which are not shared by their hyperonyms. As you can see in the example, we can say the dog is barking, but it's very strange. I mean, it's semantically correct, but pragmatically it would not be correct to say the animal is barking. Yeah, so you would say the animal is calling or making sounds. Okay, so now related work, I think I will skip this part. It will be available in the slides and also with a long list of the sources used. Now let's just skip to the approach to hyperonymy extraction that we use on our data. First, I specified the data set that we use so far for training and testing this model. So our data corpus at the moment is composed of around 20 million of English sentences that we scraped from mainly tech blogs for this task for 2019 to 2021. Some data characteristics are that since these are technological or even scientific blogs, it is professional writing that's relatively clean, it's curated, and also it's quite focused on technology. So it's a very domain-specific data, not domain-specific in the sense that we only look at AI data or let's say only cybersecurity data, but domain-specific in the sense that it's focused on all these concepts around emerging technologies. It's a mix of tech and business content, because obviously if you have blogs like TechCrunch and VentureBeat and all these things, then you not only find the news about new technological developments, but also about the financial actions related to these developments. And what's linguistically important here is that this data contains many named entities. Many of them are unknown. So things like new companies, but also things like a new, let's say, neural network, for instance, or a new cyber attack that just came up in the data, and also many multi-word expressions. And that's generally a feature of technological terminology, that people not always reinvent the wheel, linguistically speaking, but for instance, if you have a neural network, then next month you will have the convolutional, the recurrent, generative adversarial, and so on neural network. Yeah, so they are just expanded with more and more basically modifiers in front of the head. Okay, so now a quick summary of the approach that we use on this data. It's an approach in, let's say, 3 steps plus the pre-processing step, which is very important. So first step, linguistic pre-processing. Then the second step is rule-based bootstrapping of co-occurrent hyponym-hyperonym pairs. The third step is using distributional similarity to identify potential hyperonymy candidates without co-occurrence. And the fourth step then is asymmetry as context specificity. Good. For the pre-processing, so our general aim for this task, let's say it's a very linguistically and semantically so it's a task that requires a lot of linguistic and semantical information. That's why here we apply, so we apply POS tagging, we apply dependency parsing, and additionally we also chunk collocations and multi-word expressions. So the goal here is really to not to reduce the complexity of the data and to strip as much as possible of the stop words and so on, but rather to encode and also keep a maximum of the linguistic structure and the information in the data. Then second step, the rule-based bootstrapping. Here we actually have made a very interesting observation already some years ago. And the observation is that, so as said, rule-based bootstrapping is about co-occurrence of hyponyms with their hyperonyms. And we have made the observation here that expression of hyponyms changes over the lifetime of the hyponym. So specifically, when a new very specific concept appears, then it tends to occur with its hyperonym. That's because the author obviously wants to somehow explain the concept and allow the reader to classify the concept and to categorize it correctly. But then as the concept becomes established, the frequency of the co-occurrence decreases, because then authors in turn want to reduce the redundancy in the data. They want to write shorter, more concise texts and so on. So here, for instance, we have an example set from some years ago. So we have an example from cybersecurity on cryptojacking. So what is cryptojacking? It is a cyber attack that started in Q4 2017 as the malicious use of a person's computing power and so on. Yeah, but already you see that it's very natural to say cryptojacking is a kind of a cyber attack. Yeah, so that's what you would normally say or write when you assume that your conversation partner doesn't know the term. And so basically here we made the observation that, so in the chart, you can see two things. So first you can see the proportion of the co-occurrences and how it changes over time. So the gray portion in the chart, the gray area is basically the proportion of the co-occurrence instances, and the red one is that of the non-co-occurrences. Well, basically the occurrences of the hyponym when it doesn't co-occur with the hyperonym. And you can see that this, the non-co-occurring occurrences are basically increasing over time. And the line here shows the average distance between the hyperonym and the hyponym in words. And you can see that again here over time, so the average distance is quite small at the beginning, but then over time it increases because the context window just gets bigger, and the association between the two concepts in the text is basically much looser. Okay, so, and based on this, we know for ourselves then when a new technology comes up, when a new technological concept comes up, then co-occurrence is actually really a good way to capture it and to catch it in the data with a high level of precision, because of course, once we use the rules, then we can increase the precision. And based on this observation, we also achieve quite a good coverage here. So coming to the approach, in terms of rule-based bootstrapping, there are two mechanisms that we use. One is the heuristic patterns that are characteristic for hyperonymy. So this is a set of around 70 patterns that has already been formulated in the 90s, but then has recurred in the literature quite often, also in the past years. So these are patterns like X such as Y and other X, Y is a kind of X that, and so on. That's one thing. We formulate them, maybe also an important point, not in terms of the surface patterns, but then really based on the dependency process and basically based on their dependency structure done in the sentences. And the second point is also, since we have so many multivariate expressions, we also use the fact that when you have a collocation of, let's say, noun modifier and noun head, or adjective modifier and noun head, then it's very often the case that this collocation actually entails the head. For instance, as we have it in the example of a security breach, which is also a breach. Yeah, and this is something that occurs very frequently with collocations. And the second, even more interesting observation here is that in many cases, actually just the use of the modifier will already entail the head. So something like denial of service attack, and then entails attack. But then if you just use denial of service, then it actually also does entail attack. This doesn't work for all the cases. So for instance, in terms of cyber attacks, we would have downgrade attack, which does entail attack. But if you use just downgrade, then it wouldn't entail attack. Yeah? But as long as you have a high enough distributional similarity, so in this case between denial of service and attack, then you can also assume that this is a good hyperonymy candidate. Good, so that was the treatment of the co-occurrences, especially at the beginning of the life cycle of a hyponym. Now comes the third step, the distributional similarity. So here we use dependency-based word embeddings. Why dependency-based? Because of course we are looking also to capture the functional and the syntactic similarities between the terms, which really play a big role for hyperonymy. And here you can see an example from the cybersecurity domain. So this is a chart which shows us the most similar neighbors for attack in the sense of cyber attack in this data, because this is really like this would really be more focused on the on the cybersecurity attacks than on the physical attacks in that sense. And you can see the nearest neighbors. So the red points here are the hyponyms. And additionally, we also have other kinds of lexical relations. So we have like instances of specific categories like WannaCry, Stuxnet, Petya, and so on. So these would be actually the individuals, or if we use a real knowledge graph. We have synonyms like cyber attack, like infection, rather a near synonym maybe. And then we have some other instances like attacker, cyber criminal, exploitation, and so on. So what are the observations here? The first one is that we do catch a lot of the hyponyms, but on the other hand, obviously it also shows a lot of other lexical relations. So it does learn like very focused domain knowledge. Let's say that all these concepts and all these words do have a place in our taxonomy for cybersecurity domain, but it doesn't do this differentiation that we need between the hyponyms and then other semantic relations. And this is why here we add our first step, which is basically about using asymmetry to determine the directionality and the specificity of in a specific candidate pair. So what is the main assumption here? It is that obviously hyperonyms are the higher level categories in our taxonomy, so they're also semantically more general than the hyponyms, and thus they're also assumed to occur in more general and less informative context, whereas the hyponyms occur in more specific contexts. And this is something that can be measured and and basically evaluated using context entropy as a measure for the specificity of each of the terms. So there has been a score that has been proposed already some years ago by Santos et al. It is called SLQS, not SQL, but SLQS, which is a context specificity measure for hyperonym discovery. And how it works, it's actually a very simple process. So basically you take each word in your candidate pair, and then for each of the context of this word, you compute the entropy of the context, and then for each word, again, you compute the median of all its contexts, and then the term which has the higher median and context entropy is supposed basically to be the hyperonym in the considered pair, and the hyponym in the considered pair, and the one with the lower entropy is then considered the hyponym. And this is the last step so far in our approach. It doesn't close all the gaps, so it definitely is good at discovering directionality in potential hyperonymy pairs, but it's still well, I have to say that it still doesn't discriminate for other lexical relations also for 100%. So this is something that we are planning as the next step here. Okay, so I'm coming to the end. Just to sum up, so I presented a hybrid approach to hyperonymy discovery, which benefits from the lexical and the linguistic characteristics of hyperonymy. It goes in 3 steps. So first, we use lexicosyntactic patterns for bootstrapping on co-occurrences of hyperonymy pairs. Then we use distributional similarity to capture the nearest neighbors of hyperonyms and also of co-hyponyms. And finally, we apply this approach based on entropy and context specificity to determine the directionality in candidate pairs. Nice feature here, as said, it's really good aligned with the temporal evolution of new hyponyms. which can be captured by the patterns due to their frequent co-occurrence with hyperonyms at the beginning of their life cycle. So challenges and future work beyond this challenge that I mentioned of discriminating even better between the different lexical relations. Of course, we also actually want to follow a more inclusive approach and also to include other lexical relations in the construction of taxonomies, or in this case, it would also go more into the direction of ontologies. So add more lexical relations, specifically co-hyponymy, which is actually a complement to hyperonymy detection, but then also things like meronymy, so the part of relation, synonymy, and antonymy. And finally, a challenge that we are also facing now. So far we have been talking about technology, which is a very, let's say, well, quite discrete domain with very clear formulations, definitions, and so on. But we are also seeing demand in domains that are much less well defined and more vague. So when I was answering Manuel's questions, for instance, I mentioned this domain of sustainability or ESG, so environment, social, and governance. And this is like a very, well, it's a very new domain, thus it's not well defined so far. And it's also in some way artificial, in that it's actually a domain which is created specifically for the financial industry. And you could see that, okay, if it's so vague and so on, then why do we need to use a taxonomy for this? But on the other hand, there are taxonomic standards that are assumed. So it's always, yeah, it's a balance act basically here to find the right level of structure that you want to use for these cases of more vague domains. Good. I think that was the summary, and now I would be looking forward to the questions.